Right, great. I'm Jenny Gillenwater, and I'm going to talk about a differential privacy system that we've built and maintained at Google over the past few years. We call the system Plume. So its core code is written in Plume, which is Google's framework for MapReduce computations. We dropped the F from Plume and we put in a P for private to get Plume. And in January, we posted this paper on arXiv, mostly focused on one optimization of the Plume system. And it can be found at the link given there. And then the arXiv paper describing this work is also authored by Karim Amin, Matthew Joseph, Alex Kuleza, and Sergey Vasilitsky. So I'll mostly talk today about the contents of that paper. And before I go into the details, I'd like to note that in addition to the authors of the arXiv paper, there have also been a number of other contributors to the coding and the planning of various components of the Plume system. And this full list of contributors can also be found in the acknowledgement section of the arXiv paper. So currently Plume has over 100 client teams within Google, and they're currently using the system to compute private statistics, so counts and sums and means and quantiles of user data. And just to be clear, it's not a machine learning system, it's just a system for computing these types of basic statistics. And then individual client teams are often in charge of a number of data sets for which they run pipelines to produce private statistics, and that adds up to thousands of pipeline runs a week and petabytes of data processed. And the individual data sets themselves routinely consist of trillions of records. So Plume enables the teams that manage those data sets to share statistics about them more widely. For example, in 2020, Google's public and environmental health team used Plume to release data related to COVID-19 search queries. And this was a data set for which the team received public thanks from government officials, like this letter from the Director of Communications for the UK Prime Minister's office. In developing Plume, we consistently found that, to apply DP to Google's data sets, it wasn't sufficient to just give teams, say, a parallelized implementation of Laplace noise or Gaussian noise, because that left a few issues unaddressed. So first of all, we faced the issue that most data sets didn't satisfy the common assumption from the DP literature that a user only contributes a single record. And instead, typically users were making multiple contributions. The number of contributions varied from user to user. So in order to not violate the privacy of a given user, we needed to assume that the DP neighboring relation involved adding or removing all of the user's data. And then to make it simple for teams to apply this kind of DP to their data, we had to implement contribution bounding infrastructure for this. And given some fixed epsilon and data that were required for privacy, this kind of infrastructure also allowed teams to experiment a little with different contribution parameters to find a good bias variance trade-off for their results. And then the second major issue that we found teams needed support for was key selection. So there were a lot of data sets where the set of possible values for a record was not simple or efficient to specify. And instead, we needed to provide some infrastructure for supporting key selection based on the data set itself. So both these components, the contribution bounding, the key selection, they were vital to making DP usable in practice. But we didn't have to develop really any original theory to do these. What we mainly faced challenges in was making these two components scale well to large data sets while maintaining good accuracy. So is this good scalability accuracy balance? That was one of the technical contributions of Plume and what I'll mainly focus on today. To put Plume in context a little with some other systems before we dive into details, Plume works in the central DP model where all the private data has already been collected on some central server. And this slide lists a few other central DP systems used by various companies. So for Pink and Flex, one key difference distinguishing Plume is that it explicitly handles the multiple user contributions. So it provides infrastructure for teams to enforce contribution limits. And then similarly, you've got LinkedIn's audience engagement API, and it handles one specific multi-contribution setting, which assumes that users can contribute sort of once to all keys in the data. But unfortunately, this didn't cover a lot of use cases for Google datasets, especially when users tended to contribute to some small sparse set of keys. Google's DPSQL and privacy on bean systems, they handle multiple user contributions. But as we'll discuss in a little more detail later on, Plume makes a different accuracy efficiency trade-off than these. So in particular, the Plume system sacrifices some efficiency to increase result accuracy. As a running example, consider the task of computing the frequency of each Google search query in some query data set. And then the non-private solution in this case can be implemented in a standard MapReduce framework by a group by followed by a count. For a private solution, if we just replace the count with a noisy count, that doesn't address the contribution bounding and the key selection issues that we just discussed. So some users may have contributed a lot of different search terms to the data set or searched the same term many times, and we need to limit the total number of contributions for any given user so that we can determine the sensitivity of computations. And similarly, we can't just output a count for all the queries in the data set because that might reveal a search query that uniquely identifies an individual, and we can't efficiently enumerate all possible search queries, so we can't just output a noisy count for each possible search query. So let's talk about one simple way of addressing both of those issues in a practical system. We'll use A to denote the desired aggregation, like count or sum or mean or quantiles. And we'll want the framework to be generic enough to handle all of those. D will represent the data set, composed of key value pairs, also tagged with user IDs. And for the simple query counting example, the keys are going to be user search query strings, and the value associated with the key might be the number of times that a user has searched for a particular query string. And our goal is to apply a mechanism M, providing user-level privacy in the add-remove model. So you can think of M as, the Laplace mechanism for simplicity, but it can really be any mechanism that can be run in parallel on each key of the data set. So in Plume's current iteration, we have Laplace, we have Gaussian, and we have some exponential mechanisms. So depending on the type of mechanism, there might be different contribution bounding requirements. For Laplace, you need to know a limit on the L1 norm of the vector of user contributions to all keys. For Gaussian, you need a limit on the L2 norm. And for different exponential mechanisms, you need different things. But for the one that we apply for quantiles, you need some max on the number of keys contributed to. You need some limit on the number of contributions to each key, and then some min value, max value range for each contribution. So to handle all these within one framework, we enforce two generic limits. So first, we enforce a limit L on the number of keys to which a user can contribute. And then for a given key, we have some limit C on either the magnitude or the number of contributions to that key. So notice that we can combine L and C to bound either L1 or L2, which is shown at the bottom there. And we can also get most of the necessary limits for the exponential mechanism on quantiles from this. And the other ones are actually very, very easy to enforce. So by enforcing these two limits, we can characterize sensitivity for a lot of mechanisms. And in the next few slides, I'm going to talk about several alternative system designs operating in a MapReduce framework. So just to review, in this framework, input records are initially divided arbitrarily among workers, and then the computation proceeds in rounds. And in each round, we have these three phases. A worker first independently processes each record in its local collection, and that's the map phase. And then the processed records are going to be redistributed so that records with matching keys are located on the same workers. That's the shuffle phase. And then finally, the shuffled records that are associated with each key are processed as a group by their local workers, and that's the reduce phase. So since the shuffle phase requires moving large amounts of data across relatively slow channels between workers, it's usually much more expensive than the map and the reduce phases. So the number of shuffles is usually a good first order predictor of a MapReduce system's runtime. So minimizing the number of shuffles tends to reduce runtime. These are the three systems that we'll discuss. RuntimeOptimized is a system that prioritizes runtime. at some expense to accuracy. Naive places greater priority on accuracy, but is slow. And then the system we call Plume represents a better balance of runtime and accuracy. So it essentially achieves naive's accuracy, but with speed closer to that of runtime optimized. So then after going over the systems, we'll wrap up with a few experiments comparing them. So first, the runtime optimized system. It's a very simple system. It's only going to have 2 shuffles. It's going to enforce the LNC limits. It's going to do key selection, but it's going to do so in a way that sometimes can greatly prioritize efficiency over utility of the system outputs. So the system is actually very similar to how Google's DP SQL system functions. And it begins with a MapReduce that groups the data by user, and it limits each user's contributions to L keys. So internally, this is done with a heap that has a key limit of L. And note that, although it's not shown in the pseudocode, we can also store alongside each key in the heap a summary of the user's data for that key. So for instance, if we're doing a count of search queries, we can store the total number of times that the user issued a particular query. And then we can use, yeah, sure. Sure.
What's the result of random or
when there are many queries, what's the result for enforcing L? We randomly select. Yeah, that's a good point that that's also a design choice though. And then let's see. So if we also have, the values in here as well, so we have maybe like the total number of times that the user has issued a particular query, then we can easily cap that at some max value C during heap merging, and that doesn't really add any significant overhead. So the difficult things to make scale here is really contribution bounding of that L parameter that controls things across keys. Then you've got one additional MapReduce for the remainder of the system, and the data in this case is grouped by key. So you can see a shuffle on keys at the bottom there. So then we're running a key selection algorithm, DP retain key in the code here. And it's run on the count of unique users for a given key. So typically this algorithm will do something like add Laplace noise with scale epsilon divided by L, and then it'll return true if the noisy count exceeds a certain threshold. Then for any key that passes that if statement check on the DP retain key, it makes it through the key selection process, then the associated data is passed to the core DP mechanism M, and that could be anything like, could be like a Laplace mechanism, but the Laplace mechanism in that case would add noise with scale epsilon divided by L times C. You contribute to L keys and a max of C for each key. So, we could also have Gaussian or exponential mechanism slotted in here instead for something other than a count. This runtime optimized system is really efficient because it only requires 2 shuffles, but it can have accuracy issues. So consider a toy dataset where records represent visits to specific locations. And each user in this toy dataset visits exactly 2 locations, their home location, which is unique to them, and a popular landmark, which is visited by a lot of other users. And if we want to count visits to locations here, and we set the bound L at 1, then contribution bounding will discard half the visits, and all locations can expect to be undercounted by a factor of 2. And this is, like you point out, this is if we randomly select which location to keep for each user. So given enough users, the landmarks will have enough visits to survive key selection, but no matter how many users we have, the undercounting will mean that the outputs will have a relatively large error of about 50% compared to the true counts. And one straightforward solution to this problem is to redo contribution bounding after key selection. So before we run the DP mechanism M, we go back to the original data, we enforce the L limit again, but this time we only keep user contributions to selected keys. And that way a user isn't wasting contributions on other keys. And with this setup, each user will contribute to a popular landmark that made it through key selection, and they won't waste a contribution on their home location. So this is a pretty contrived example, but we see the same effect whenever the frequency of keys and data follows some kind of long tail distribution. So if each user contributes to some keys that are relatively common and then some that are relatively rare. So let's talk about a naive way of doing the second round of contribution bounding, and then we'll show how to make it more efficient. So the first phase of this system is nearly identical to the runtime optimized system that we already covered. It has two shuffles, one to group by user for enforcing the L limit, and one to group by key for running the key selection algorithm. And the key selection phase can't be done in the same MapReduce round as the aggregation phase anymore, because remember that before applying the mechanism M to each selected key, we want to redo contribution bounding based on this privacy-safe key set S. So what we can do instead is we can run a join operation on D and S. That is, we're going to restrict D to only its entries that are keyed by something from S. And that requires shuffling D's data to group it by key. And then finally, we're going to take this S restricted data set, the D sub S, and we're going to group by user to enforce the L contribution bound again. And now we're going to group by key to run our mechanism M on each key and output the result. So in contrast to the contribution bound once runtime optimized system, which had 2 shuffles, here we have 5 shuffles. And also we found in practice that the join operation can be very expensive. And that's mostly because the join is typically very skewed. So often it's the case that the data set D is very large and it has a lot of keys that aren't in S. So S is really small compared to D. For instance, this happens if the input data has a long tail of low count keys, most of which don't make it into the privacy safe key set S. So the system can be more accurate than the runtime optimized one, but it sacrifices a lot of efficiency. And it turns out that we can solve some of these efficiency issues while retaining most of the accuracy. First, because we can substitute in a component that's almost as accurate as the skewed join, but much faster. And second, because this alternative component is going to allow us to do the group by user shuffle that appears in both phases only one time. So here's a more efficient system, which is currently implemented as the Plume system at Google. There are 2 key differences from the previous slide. First, notice that we begin by grouping the data by user to produce a data set D naught. So this grouping is going to be fed into both the key selection phase and the aggregation phase, and it removes the need to repeat that grouping work in each phase. In the naive system, we couldn't factor out this component because we had to have the data indexed by key rather than by user in order to do the restriction to S via a join. But here, we're going to replace that join with a Bloom filter. So we build a Bloom filter T on S that can be quickly queried to ask if a particular key is in the set S. Then we're going to query this during the contribution bounding part of the aggregation phase so that we can, with high probability, discard records whose keys are not in S. So let's talk about the Bloom filter in a little more detail. We make the object small enough that it can fit into memory on a typical worker machine. And this means that a copy can live on every worker and querying it's relatively fast. And the way we set the size numbers, as long as S has no more than about 1.5 billion keys, then the expected false positive rate for the Bloom filter is less than 1 in a million. And then the larger S gets past that point, the greater the chance of false positives. So what does that mean? That means that the filter will more often say that a key is in S, even though it's not. And that can lower the utility of the final system output relative to the naive system, because you're going to waste some of a user's contribution quota on keys that aren't actually in S. But in practice, we found that using the Bloom filter has given a good accuracy efficiency trade-off for a lot of data sets. So let me give a few simple experiments that kind of serve to illustrate the accuracy efficiency trade-offs here. The 3 systems we'll look at are the runtime optimized one. This is the one that did contribution bounding once and had 2 shuffles. The naive system does contribution bounding twice, but requires 5 shuffles, one of which is a really skewed join, and then Plume, which requires only 3 shuffles and no skewed joins. The experiments I'll show are just simple counting tasks, but the Plume system, again, is regularly used for some other types of statistics. And the two metrics we'll look at are system runtime and aggregation error. So aggregation error is going to be mean relative error on keys that make it through the key selection phase. And the reason we only look at these keys is because for all three systems, they do the same thing for key selection. So they should end up with the same set of keys. We fix the privacy parameters at epsilon of 1, delta of 10 to the negative 9. Half the epsilon and delta go to key selection. Sorry, half the epsilon and all of the delta goes to key selection. And then the remaining half of the epsilon goes to the aggregation mechanism M, because in this case, we're using a pure DP mechanism for M. But you could also split the delta as well and use something like Gaussian. And then for the contribution bounding parameters, we cheat here, and we choose L and C based on properties of the data. So we do a grid search to find the accuracy maximizing values for each of the three systems. And this just lets us compare the best case performance of all three. But of course, if you want to build a truly end-to-end DP system, these parameters also need to be chosen in a DP way. I'll skip some details here, but this is just, we generate synthetic data. We try to mimic the heavy-tailed nature of real data. We build data sets that have 1 billion to 1 billion users, and the largest data set contains about 10 billion records. So let's take a look at an actual plot of aggregation error. So error is on the y-axis, so lower is better. And on the x-axis, we have data set size. And we can see from this plot that Plume and naive, the curves are completely overlapping here. So they're achieving basically identical results, while runtime optimized is going to be significantly worse because it's wasting some contributions on keys that don't survive key selection. You might also notice that the curves here appear to be converging as we head to larger and larger data sets, but I think that's probably just an artifact of our particular synthetic data generation method because we fixed the total number of keys at some constant value for all the data sets. So on the larger data sets, there isn't as long of a tail of very low frequency keys. And that means that a greater fraction of the keys survive key selection, and then redoing contribution bounding after key selection is not going to make as big of a difference. In terms of runtime, on the y-axis, this is the slowdown relative to a non-private system. So that would be just a regular Plume count operation. And then on the largest data set, naive is about 21 times slower than non-private count. Runtime optimized is 3 times slower, and Plume is 5 times slower. So we've managed to bring the runtime of this contribution bound twice scheme down to a reasonable-ish level. We also ran experiments on some real data that shows roughly the same thing. This was Reddit data from a common corpus that has about 3.8 million posts. And we were trying to count word frequencies here. So performance is averaged over 12 runs. Standard errors are shown in parentheses. And again, the runtime of Plume is not too far from that of the runtime optimized, but it retains the accuracy of the naive system, which is about 64% better than runtime optimized here. So to summarize, Plume is a system we built at Google over the past few years, and it sees wide use from client teams for computing basic DP statistics. It handles some practical issues like contribution bounding and key selection in a scalable way, and it makes an accuracy efficiency trade-off that's different from that of existing systems. So in terms of future work, one big thing we'd like to do is sort of automate the tuning of those contribution limits like L and C in a differentially private manner. And then, of course, we'd also like to add, new aggregations and mechanisms to the Plume framework to incorporate, important work from the DP literature and make it accessible to all these client teams. So if you have a method that you think might be able to scale well, come talk to us. And then further in future, we'd also like to expand our infrastructure to handle things like the streaming setting.